So what exactly makes a vector? A vector. It comes down to two essential properties: magnitude and direction. These are the defining characteristics that set vectors apart from ordinary numbers. Let us start with magnitude. Think of magnitude as the size or strength of something when you picture a vector as an arrow. The length of that arrow represents its magnitude. A longer arrow means a larger magnitude. A shorter arrow means a smaller one. It is that straightforward. Now for direction. Every vector points somewhere. The arrowhead shows you exactly where. If you have an arrow pointing north, that is its direction. If it points northeast, that is its direction. The arrow always points from its tail end to its head, giving you a clear sense of where the vector is headed. Here is something really important to understand. Two vectors are considered the same if they share both the same magnitude and the same direction. This leads to a fascinating property: you can slide a vector anywhere you want, move it up, down, left, or right. As long as you do not rotate it or stretch it, it remains the exact same vector. The position does not matter, only the magnitude and direction matter. This might seem strange at first, but think about it this way: if you push a door with a certain force in a certain direction, it does not matter exactly where you are standing when you apply that push. What matters is how hard you push and which way you push. Now let us contrast this with something called a scalar. A scalar is just a fancy term for a regular number. Scalars have magnitude but no direction. Temperature is a good example. If someone tells you it is 70 degrees outside, that is a scalar. There is no direction involved. Weight is another scalar. Speed, on the other hand, becomes a vector when you add direction, which we then call velocity. There is one special case worth mentioning: the zero vector has no magnitude and therefore no direction. It is the only vector that breaks the rule about having direction, simply because there is nothing there to point anywhere. Now that we understand what vectors are, let us talk about how we write them down. This might seem like a small detail, but having clear notation is essential for communicating mathematical ideas effectively. When you see vectors in textbooks or printed materials, they are almost always written in boldface. A vector would appear as a bold lowercase a or b. This convention makes it easy to distinguish vectors from regular numbers. At a glance, your eye immediately knows that bold A is a vector, while regular italic A is just a scalar. But here is the problem when you are working through problems by hand. Who has time to write in bold? It is not practical. That is why mathematicians developed an alternative system for handwritten work. Instead of boldface, we place a small arrow above the letter, so vector A becomes A with an arrow over it. This achieves the same goal of distinguishing vectors from scalars, but it is much faster to write. Sometimes we need to be even more specific about where a vector starts and ends. In these cases, we use what is called terminal point notation. If a vector starts at point A and ends at point B, we write it as AB with an arrow on top. This tells you exactly what the vector looks like and where it is positioned. For more advanced work, especially in 3 dimensions, we have the standard form representation. A vector can be expressed as A equals A times I hat plus B times J hat plus C times K hat. Those little I, J, and K with hats are called unit vectors, and they point along the x, y, and z axes respectively. The numbers A, B, and C tell you how far the vector extends in each direction. There is also a cleaner way to express this same idea. We can write vectors as ordered pairs or n-tuples. A 3-dimensional vector might simply be written as 3 numbers in parentheses, and for those working with coordinate systems, we have basis vectors that point along each axis. These are written as E1, E2, and E3, each pointing purely in one direction. Now here is something fascinating. In the world of vectors there exists a true oddity. A rebel that breaks the very rules we just established. It is called the zero vector. Remember how we said every vector has both magnitude and direction? Well, the zero vector is the one exception to this rule. It is the only vector in existence that has zero magnitude. Because it has no length, it cannot point anywhere. And if it cannot point anywhere, it has no defined direction. Think about that for a moment. Every other vector, no matter how tiny, stretches out in some direction. But the zero vector, it is essentially a point, a vector that goes nowhere. We write it as a bold 0. And here is something remarkable about it. There is only one zero vector. This makes it completely unique among vectors when you think about it. Regular vectors can point in infinitely many directions with infinitely many possible magnitudes. But there is only one way to have zero magnitude. So there is only one zero vector. This solitary vector plays a crucial role in vector mathematics. It serves as what mathematicians call the additive identity. That is a fancy way of saying that when you add the zero vector to any other vector, nothing changes. If you have a vector representing a force or a velocity, and you add the zero vector to it, you get back exactly what you started with. In a sense, the zero vector is both nothing and something at the same time. It has no magnitude and no direction, yet it exists as a perfectly valid mathematical object with an important job to do. It reminds us that even in systems with strict rules there is often room for one special exception. Now let us explore how vectors actually combine. This is where things get really interesting. Adding vectors is not like adding ordinary numbers. You cannot simply stack them together and call it done. Instead, we use something called the tail-to-head method. Here is how it works. Imagine you have two vectors. Let us call them vector A and vector B. To add them together geometrically, you take vector B and slide it without rotating it until its tail sits exactly at the head of vector A. Remember, sliding a vector around does not change it at all once you have positioned vector B. This way, the sum of A plus B is simply the new vector that starts at the tail of A and ends at the head of B. This might sound abstract, so let me give you a real-world example. Picture a car driving due north at 20 miles per hour. Inside that car, a child in the back seat throws an object eastward at 20 miles per hour. Now here is the question: what is the actual velocity of that object relative to the ground? The answer lies in vector addition. The car's velocity is a vector pointing north. The throw adds another vector pointing east. When you place these vectors tail to head, they form a right triangle. The combined velocity, the sum, points northeast and forms the hypotenuse of that triangle. This is the beauty of the tail-to-head method. It gives us a visual way to understand how velocities, forces, and other vector quantities combine in the real world. Now let us get practical. How do you actually calculate the magnitude of a vector when all you have are its components? The answer comes from a formula. You might recognize it. Looks almost identical to the Pythagorean theorem, and for good reason. If you have a vector with components x, y, and z, its magnitude is the square root of x squared plus y squared plus z squared. Think about why this works in two dimensions. Your vector components create a right triangle. The x component stretches horizontally, the y component stretches vertically, and the vector itself forms the hypotenuse. The Pythagorean theorem gives you the length of that hypotenuse in 3 dimensions. You are just extending the same logic outward. Here is something important to remember: the magnitude is always a scalar. It is just a number. No direction attached. Even though your vector might point northeast at a 30-degree angle with components of 5 and 3, its magnitude is simply a value about 5.8. In that case, this scalar nature makes magnitude incredibly useful in physics. When you calculate the magnitude of a velocity vector, you get speed, pure speed, without any information about which way the object is moving. When you calculate the magnitude of a force vector, you learn how strong that force is regardless of its direction. Now, some vectors are special. They have a magnitude of exactly 1. We call these unit vectors, and we mark them with a little hat symbol above the letter. These become incredibly handy as reference directions, but that is a topic we will explore soon. Now let us step away from abstract mathematics and explore where vectors truly shine. The physical world around us is filled with vector quantities that govern how things move and interact. Consider velocity. When you are driving, speed alone does not tell the whole story. You could be moving at 60 kilometers per hour. But are you heading north, south, east, or west? Velocity bundles speed together with direction into a single powerful concept. This is why navigation systems can calculate your arrival time so precisely. They know not just how fast you are going, but exactly which way. Force works the same way when you push a heavy box across the floor. The result depends on both how hard you push and the angle at which you apply that push. Push straight on, and the box slides forward. Push downward at an angle, and some of your effort gets wasted pressing the box into the floor rather than moving it. Displacement and acceleration follow similar rules. They all carry that crucial extra piece of information: the directional component that ordinary numbers simply cannot capture. The word vector itself has a fascinating origin. It comes from Latin meaning carrier, and that is exactly what these mathematical objects do. They carry information from one point to another. Describing journeys through space, 18th century. Astronomers were among the first to recognize the power of this concept. While studying planetary motion, they needed a way to describe how planets moved through space over time. The directional nature of movement demanded a new kind of mathematical tool. Then, in the late 19th century, researchers investigating electromagnetic induction expanded vector use even further. They discovered that electric and magnetic fields had both strength and direction, making vectors the natural language for describing these invisible forces that power our modern world.